thank you for the organisers. This is my first time to Sweden, at least as an adult. I've been told I was here when I was 1. I don't quite remember that. I want to talk a little bit about work we have done last year. This is a relatively new field for us. Hopefully it's not going to flicker like this all the way through, is it? Just to motivate this work, I wanted to first introduce some of the areas we've been working on before getting into machine learning. We are, as a group, interested in photochemistry and photobiology. That is, how do complex systems, chemical or biological, respond to the absorption of light. And we've been studying fluorescent proteins, particularly in their response to UV radiation. We've been looking at some DNA damage. We've been looking at chemical systems such as solvated electrons. These are highly reactive, reductive species that are generated from the radiolysis of water, and some photosynthetic reactions. And in all of these systems, we are interested in being able to predict what happens after the absorption of light, which means that we need to understand the key potential energy surfaces. We've heard about this already this morning. The challenge, of course, in photochemistry is we need to consider multiple electronic states. And we also have to deal with the breakdown of the Born-Oppenheimer approximation. The electronic states will be coupled through motions of the nuclei through the non-adiabatic couplings. And so the approach we take is to solve and understand the dynamics in complex systems is that of ab initio multiple spawning, a method developed by Todd some time ago. But what we like about it is a sort of systematically improvable approach to excited state dynamics, rather than surface hopping where you get the answer that it gives. Multiple spawning, you can increase the number of trajectories, and that will improve the description of the dynamics. And so the idea is you want to expand the time-evolving wave packet in a trajectory basis that describes the motion of the wave packet, and basically you can think about it as a basis set expansion that follows where the wave packet is moving. It's an adaptive basis. And those basis functions follow classical trajectories, F equals ma, so we can use our usual molecular dynamics algorithms to propagate those basis functions. And then we can solve the potential energy surfaces on the fly. This is the standard old-fashioned approach, and that means doing electronic structure calculations at every time step, solving for the potentials, the forces, and the couplings. And then the population transfer between basis functions occurs through the solution of a time-dependent Schrödinger equation. Okay, and so how then do we actually get the potential energy surfaces? Well, what we'd like to be able to do is a very high-level electronic structure theory calculations such as equation of motion, coupled clusters, singles, and doubles. But we all know that this computational scaling of that with the system size makes it prohibitive for anything but small molecules. And for example, if you wanted to compute the energies and gradients of a DNA, you may be okay with a thymine, but as soon as you get to adenine, you're already the cost of hours per time step, and my students do not have that much patience to wait for simulation results. So what we'd like is to be able to get simulations in the minutes, and that would allow us access to picosecond time scales. That's typically what the experimental time resolution time scales are. Okay, so one approach is, of course, develop electronic structure theory and come up with something rather fancy, such as a linear scaling flavor of coupled cluster. However, most linear scaling methods come with very high prefactors, meaning that while we can maybe treat DNA molecules in the minute time scale, as soon as we get to something like chlorophylls, we're out of range, and particularly if we want to treat an entire protein, there's no way. Perhaps maybe with even if we were to reduce the quality of the electronic structure to TDDFT, a full protein is still out of the question. And so I'm going to give you a little bit about what we've been doing the last few years before talking about machine learning. And we've been tackling this problem from another perspective, which is to try to remove as many electrons as possible. And to recognize that many of these systems share a commonality, that there are a few chromophores that are responsible for the light absorption, the DNA, or the chlorophylls, or the chromophore of the fluorescent protein. So we can focus the electronic structure calculations on those active regions and take advantage of highly developed force fields, particularly polarizable force fields, to treat the rest of the protein matrix or the DNA backbone. Okay, and so we've done a lot of development recently to make polarizable embedding work with photochemical simulations. Particularly, we find issues with the description of conical intersections. We heard about those earlier in Ignacio's talk. They're poorly described. There are artifacts with many polarizable embedding methods. We've extended an old version of one to actually get it working with conical intersections. And we've also done some development to be able to include solvent in the QMMM region, in the QM region of a QMMM calculation, without problems of boundaries deteriorating over time. Okay, so this is old stuff, and I know I shouldn't talk too much about this because this is a machine learning audience. And so really where we're going with this is to try to completely remove all of the electronic structure calculations. That's what we'd all like to do here, because then we can remove any of these horrible bottlenecks and have energies and gradients on timescales of seconds, allowing us to push the simulation lengths to nanoseconds with perhaps very complicated molecules. Okay, and so we've actually heard already today about learning potential energy surfaces. There's many approaches, and you might think, well, why can't we just do the same thing but for electronic excited states? Well, the challenge here, we've already heard it again from Ignacio, is the problem of electronic crossings. And these are going to be ubiquitous in photochemical and photobiological systems. The potential energies cross, and at that point, there's a derivative discontinuity in the adiabatic surfaces. There are kinks, cusps, that of course give severe challenges to the typical smooth functions that underlie kernel methods or the activation functions that used in neural networks. They will be unable to describe that kink. Okay, and so what can we do? Well, of course, we're not the first to think about this problem, and there's several approaches that people have taken. One is just to live with it, okay? Say, well, we're never going to perfectly describe that kink, but maybe it doesn't matter. Maybe your dynamics actually will hop to the lowest state before it ever reaches that region. So that actually works quite well with surface hopping. It turns out not to work well with multiple spawning, because in that case, you're treating multiple trajectories running on the adiabatic surfaces, and you need a good description of potential energy surface everywhere. You don't have the hopping that sort of skips the problematic region. Another approach that people have taken is to switch to use activation functions with actual discontinuities, which is an interesting approach, but of course requires you to know where the conical intersection is a priori, and in complex systems that's of course impossible. Another approach is to switch back from the machine-learned surfaces to ab initio calculations when you get close to the crossing. And of course that approach will work, but it comes with computational cost and a lot of code complexity. You have to build the machine learning model inside your electronic structure calculation. And then what we heard about this morning, I don't have to talk too much about it today, is to switch to a diabatic representation where you no longer have, you have now off diagonals in the electronic Hamiltonian, and these diabatic surfaces can maintain character and be smooth. This is obviously a very nice approach, but it tends to be quite system specific about whether it's going to work. You need to know a lot about the system, the number of states that are crossing, etc. We would like to try to stay in the adiabatic representation, right? That's what the electronic structure calculations are giving us. They're giving the energy ordered states. Can we learn them directly? And so the idea we had is to start from density functional theory, because the Hohenberg-Kohn theorem tells us there's a one-to-one map between the external potential of a molecule, that's the electron-nuclear interaction, and the electron density of the system. And because the electron potential completely defines the Hamiltonian, that means the density can also tell us something about all of the electronic states of the system. What we want to do then is to extend the Hohenberg-Kohn theorem to be able to treat electronic excitations. And there has been some good arguments in the literature. I wouldn't say there's been a proof, but there's an argument that the Hohenberg-Kohn theorem can be extended for excited states, particularly for, specifically for Coulombic system. And the argument goes as follows, that the tails of the electron density for different electronic states decay in a manner that's dependent on their energy. Okay, and that those tails of the density then are related to one electron orbital, since you will only find a single electron far from the molecule at a time. And from that, there's arguments there should there be a universal functional that describes the energy of the system and how it's related to the density. And that argument was made by Paul Ayers, Levy, and Nagy. And that forms the basis for orbital optimized density functional theory, which is very successful and, for example, is used quite a lot by Martin's group recently. Okay, so with that idea in mind, then what we can do is to learn a map from external potential to multiple densities to a single energy functional that takes a density and gives us an energy. And the hope with doing so is that we will be able to describe electronic crossings more accurately than if we had a single map from a descriptor to an energy. And we're going to see this has some legs to it. All right, so we want the molecule that we're going to consider and apply this to is malonaldehyde. The reason we chose this molecule, not only is it quite simple, but it has some complexity. It has an intramolecular proton transfer. The hydrogen can transfer from one oxygen to the neighboring oxygen. And on the ground state, there's a barrier of about 7 kilocalories per mole. So this is a tunneling reaction on the ground state, but in the S2 excited state, which is a pi star transition, the barrier essentially disappears. And so this excited state proton transfer could become ultra fast. However, there is another process that occurs on the excited state, which is internal conversion, which actually outcompetes the intramolecular proton transfer, meaning that you actually don't observe a proton transfer event in malonaldehyde. Okay, and that's because the lower electronic state has a much higher barrier of about 30 kilocalories per mole. So in applying our ideas, what we want, the key scientific question we would like to address, in addition to developing methodology, is how can we use mechanical constraints to promote excited state intramolecular proton transfer in this molecule. And the idea is that the conical intersection responsible for the internal conversion has a lot of twisting in the backbone, and so if we can maintain planarity in the molecule, perhaps we can reduce the rate of internal conversion and then promote proton transfer. So here's the model. We are learning densities, and so we express those densities in a Fourier basis, which is particularly convenient if we're using electronic structure in a plane wave basis. And we want to learn the Fourier coefficients then. That will give us the densities for each electronic state. And we're going to use kernel ridge regression here. Of course, this could be done with neural networks, but we really want to, as a proof of principle, test the idea of constructing a multi-state functional and improving the description of energy predictions in the vicinity of electronic crossings. And so the kernel ridge regression, we just have to solve for the coefficients for each of the Fourier bases. For each individual wave vector, we have our own kernel equations that are solved. And then once we know the densities, then we can predict an energy functional in the same manner. And the idea being that energy functional can take multiple different state densities and return their respective energies. So we have a single model that can predict multiple electronic states. And the training data we get from running ab initio dynamics on the S2 excited state and then extracting some snapshots, augmenting the data to characterize the symmetry of the species, the reflection and rotation symmetries, but then clustering down the data to avoid a very large data set. And then we use a pretty standard approach of hyperparameter optimization, and we make sure that any test sets we apply the model to are not in the training set at all. Okay, so first of all, let's look at how the model does in predicting densities. And so we can actually see a very good agreement between our predicted densities and time-dependent density functional theory. I should point out, TDDFT, of course, is not very accurate at the barriers for this molecule. Again, this is more of a proof of principle study here. But what we can find is that we get accuracy in the densities to about 0.01 electrons here, so we're almost perfectly reproducing them. And we're looking here at the density differences. That's how the density changes upon excitation. And already we can start to understand why the barrier in the n pi star state is so much higher than in the ground state. It's because we're depleting the electron pair density of the oxygen that would be accepting the hydrogen bond. So that raises the energy, the barrier to proton transfer. Whereas in the pi star state, there's very little density changes involved in the hydrogen bond acceptor. Okay, so that's the density predictions. How about the energy predictions? So let's look at some learning curves first. I'm going to start by talking about the molecule in its planar geometry. And in that case, we see a very rapid convergence with respect to the number of training sets size, but we don't really see any improvement of the multi-state predictions versus predicting the energy one at a time, right? So if we had just a unique energy functional for each state, performs just as well. Okay, and we can confirm by looking at the energy predictions along a trajectory, they stay within the ab initio answers to within a kilocalorie per mole. Okay? Now we start to see the differences, however, when we let the molecule twist and approach the crossings between the electronic states. And then we see, in fact, a stagnation in the energy predictions for the single-state functionals. They plateau and never go below a kilocalorie per mole. Whereas if we use a multi-state functional, so we're predicting all of the states simultaneously, we can see we can continue to improve the energy predictions by increasing the training set. Okay, and indeed, so what's going on here? Why is the single-state prediction not working? Well, we can see it's actually starting to fail as we approach the crossing between the electronic states. So this is the problem of the underlying Gaussian kernel ridge not being able to describe kinks in the potential energy surface. But as soon as we treat two states at the same time, essentially we have data for both electronic states before and after the crossing, and we just have to energy order the outcoming predictions, and then we can actually recover a kink in the potential energy surface. And so the multi-state model reproduces the ab initio data much more accurately, even after the crossing point. Okay, so what can we learn about this molecule? Again, we wanted to see how can we promote the intramolecular proton transfer. And so our idea was to essentially freeze out that internal conversion process. And we want to make it impossible for the molecule to reach any of those twisted Courant intersections. And so we do that by applying planarity restraints to keep the molecule mostly planar. And then when we rerun our dynamics, we find the following, which is that if we're monitoring the degree of proton transfer through this coordinate r minus, which is just simply the difference in the OH bond length here and the OH bond there, and then we look to see how that coordinate has a memory through the course of the dynamics. So if that memory is 1, it means the proton is where it originally is. If it has a value of -1, it means it's transferred to the other oxygen. If it has a value of 0, it means memory has been lost and there's been multiple proton transfer events. And so what we see in the ML predictions essentially are within the envelope of the ab initio predictions. The uncertainties in the ab initio are much higher because we could only afford to do 50 trajectories. They're very expensive, whereas we can afford to do 1,000 ML trajectories, and that really brings the uncertainty error bars much down. But here's the key message I want to say, is if you just looked at the ab initio data, you may not really notice that there's a significant delay period before the proton transfer event occurs, because the error bars are so large. But that becomes very clear in the machine learning data when we can run so many trajectories, where we see that in fact nothing really happens until about 40 femtoseconds, and then there's a rapid proton transfer. And so what's actually happening in terms of the mechanism of this process is that it's not the OH bond length that is the key reaction coordinate. It's actually a distortion of the backbone of the molecule that serves to bring the oxygen atoms closer. And we can see that in our dynamic trajectories. The oxygen-oxygen distance here reduces by a few tenths of an angstrom, and once it's reached a critical value, then the proton transfer occurs rapidly. And if we look at the potential energy surfaces for the proton transfer as a function of that oxygen-oxygen distance, we see the barrier come dramatically down as the oxygens are brought together. It makes perfect sense. You bring the donor and acceptor closer, the barrier will be smaller. But it's the backbone dynamics that are responding to the pi star excitation that lead to that. So it's being gated by the backbone dynamics. And that's very much the classical picture of intramolecular proton transfer, so we can recover it in malonaldehyde by freezing out the excited state internal conversion. So I'm going to conclude there. I realize I'm a little early. I realize there's also a coffee break that I'm keeping everyone from. So to conclude, we've seen that we can generate a multi-state functional that actually performs better than a state-by-state prediction of energies and properties. And the key is to be able to include state data before and after the crossing. That seems to be what helps improve the predictions. And our simulations of malonaldehyde, the computational savings were 2 orders of magnitude faster. We were able to get dynamic trajectories in seconds rather than hours. And it's still a factor of 10 faster after you consider the cost of generating the training data. And we learned that we can enforce mechanical constraints on malonaldehyde so that the intramolecular proton transfer occurs and then follows the classical picture of excited state proton transfer developed many years ago by Zawal and co. And so there's several things we can do in the future here with this framework. We can extend it with delta learning to correct our TDDFT densities and energies with higher level calculations. And success for that idea has already been seen in the ground state from Tuckerman and Muller and Burke. We can also take advantage of the fact that we have very accurate electron densities and then use that to embed the molecules in complex environments, which would come relatively cheaply, and then allow us to get to our complex systems in biological systems. With that, I want to thank the people that did the work. My student Yuanming just graduated a few months ago. He's now working at Solvay in Shanghai. And this was done in collaboration with Mark in New York and his staff scientist Leslie. So we were supported through the strong collaborations between NYU Shanghai and New York, in addition to some funding from the Chinese funding agencies. With that, I want to just announce that we've recently moved our campus to the Pudong Qiantan area of Shanghai. If you are in town, please let me know. I'm very happy to host you for a seminar or just a look around our new campus. Happy to take questions as well. Thank you.
Thank you, William, for a very interesting presentation. I'm guessing we have a few questions in the audience.
Well, thanks for a very impressive presentation. You've been using machine learning technology to swiftly compute your energies. And you demonstrated you could now do thousands of trajectories. The particular case you showed here is a case where people who do NEO stuff, where they start to treat the protons quantum mechanically. And I was just wondering if you sort of have not thought the full process of using machine learning to use your energy functional and then use machine learning to generate an integratable surface upon which you can do, based on your classical trajectories, you can then top that off by doing it quantum mechanically too.
That's a very good idea. Thank you. Yeah, we should think about that. Yes, yeah. So speaking of Sharon Hammer-Schiffer developing NEO functionals for the protons in the system, and there may well be some accelerations that we can do there. Yes, I think we should explore that.
Hello? All right, so thank you for your presentation. Before tackling the electronic density directly, have you considered just doing this multi-state learning to the energies directly instead of not going to the densities?
Yes, I'm not sure if I showed those results. Maybe I kind of trimmed them out. Yeah, those are the orange results. So you can see they're significantly worse, even for the planar molecule where there are no electronic crossings. So seemingly, and this is what Mark found as well when they were looking at the ground state learning, that seemingly including density as an intermediate step somehow improves the energy predictions. We don't fully understand why that is though.
Okay. Maybe because the model is less prone to overfit, because it tries to generalize for both states.
Well, you're introducing a lot more parameters with the density, so I'm not quite sure. I don't understand it. So.
Okay, thank you.
So last chance before the coffee. Now we have Alexander.
Great stuff. how far we are to make this transferable?
Yes, yes. So that's what we love, right? And one of the nice things about density is there are no atoms there, right? And it's incredibly computationally invariant. So Mark has shown some degree of transferability if you learn functional groups, okay? And then multiple functional groups, and then you get some degree of transferability. I'm not totally confident this would work for electronic excitations, where the position of the electron crossing could be dramatically different with the change of functional group. But we haven't tried it yet. It's something to do.